For the last 3 terms, a small team of 4 developers, who have titled themselves Team Birdbeatz, set out to create a sound processing program that automated the grueling task of counting recorded heartbeats of wild songbirds. The team that worked on this project consisted entirely of computer science majors. The team members are as follows: Megan Black, Violet Kurtz, Kristina Marquez, and Simon Millsap. Each student brought different focuses within the domain of computer science and was interested in learning more about sound processing. The team worked on a sound analysis tool to help Dr. Jamie Cornelius and her team reduce the time it takes to analyze sound recordings of bird heartbeats. Jamie's team is researching heart rates in animals in order to learn how they cope with unpredictable changes in the environment. Things like storms, fires, droughts, etc. This is important because these changes can cause mass mortality events in different species. Her study system uses red crossbills because they feed year-round, meaning that they also breed year-round. This nature of red crossbills makes it easier to analyze effects of unpredictable events since their day-to-day life is not as severely impacted by weather conditions. Their energy expenditure can be measured via their heart rate, and observations during times of unpredictability versus times of regularity can give insights on the impact of unpredictable changes that we talked about before. The data is captured via electrodes embedded in their skin and is broadcasted to a receiver that the researcher holds while they follow the bird. Due to this method of retrievement, the data is highly noisy and thus difficult to analyze in an efficient amount of time. Furthermore, all analysis is done manually and often takes several months to complete. With the challenges of the problem at hand, the team was tasked with finding a solution that at a minimum reduced the time required to count the heartbeat data. However, the team hoped to fully automate the process with some form of computer program. During the planning phase of this project, the team was hoping to utilize machine learning techniques to help automate the counting process. However, knowing the difficulty of that plan, the team also devised a second option that would use an algorithmic approach. While discussing options with the OSU Cascades machine learning professor, Dr. Donnelly, the team realized a machine learning approach was not viable. Therefore, the team pursued development of an algorithmic approach that used scientific Python libraries to perform sound analysis on the data. This approach, along with a filtering algorithm written to reduce noise within the data, was a great success. The finalized software integrated the sound processing and filtering programs into a graphical user interface written by one of the team members to create a more user-friendly platform for the sound analysis. Now, Simon will demonstrate our finalized program.
This is what our project partner sees when they first open the application. In truth, most of our project was focused on developing algorithms to process data, but we decided to create a GUI to allow them to actually view some output. They begin by searching for a file on their computer that contains the signal data that they collected directly from the crossbill bird. Then they simply hit filter and our algorithm runs under the hood. As you can see, I've already done this, as sometimes it can take a few seconds to process these multi-hour-long files. On the left, we have the ability to select a time range that the user wants to view, currently set from 15 to 16 minutes. Now, these two sliders are more interesting here. The minimum period slider adjusts the peak counting algorithm that we wrote, so that it assumes a certain minimum amount of time that a heartbeat takes to occur. The prominence slider adjusts how strong of a signal the algorithm requires before it can be considered a heartbeat. Let's adjust the time here from 15 minutes and 5 seconds. Once we've adjusted these values to our liking, we simply hit Adjust Range. And look at that. We have some very clearly defined heartbeat peaks. If we take the period slider and increase it, we notice that some of these peaks go away. Increasing the prominence slider has a similar result. You'll notice that as we increase the prominence slider to 1, this smaller peak here has disappeared. So it's important for the user to adjust these values until they feel that they are counting all of the peaks that they want to see within this visible segment of data. In the upper left here, we record the beats per minute taken over 5-second intervals and then calculate it over the entire period selected. What this allows a user to do is first determine settings that may be appropriate for a smaller segment of data, and then extrapolate those settings to calculate the beats per minute for a larger period of time. Now let's set this to 16 minutes. The visual output becomes less useful as it doesn't tell the user much about where the peaks are occurring. But if we determined good settings for our initial segment of data, we can see that the calculated beats per minute maintain about the same value for all of our intervals. From what we see here, the overall beats per minute calculated was 497.
Overall, the project was a great success. The task to reduce the time it takes to count the heartbeat peaks was completed, and a GUI was implemented to make the analysis more succinct and efficient for the researchers. The team was aware that the software could be utilized in other research related to cardiac telemetry in mammals, and we truly hope it is shared. As for future development directions, the filtering algorithm could be further refined if the team could have access to the manufacturing documents of the electrodes themselves. At current, the best guess was assumed, and luckily it seems to be successful. But there's no guarantee unless documentation can verify. The team is happy with their results, and the project partner is happy as well.